Hi everyone. We've learned some properties about the uniform random variable and we've just learned what it was and some advanced properties about it. And now we're going to try a practice question about the continuous uniform random variable. So in this example, we're going to consider the following PDF, or sorry, CDF. I've given it to you already. It is a CDF we're going to learn about very soon. And on the right, I have already plotted a picture. I used R, but you can use lots of different softwares. Now, this CDF is defined between, well, it's defined on all of the positive real numbers, but it gets really close to one pretty quickly. So I just stopped at five, but just imagine this continues on and gets closer and closer to one. Our first part A, is to find the 80th and the 13th percentiles. Now, you might have remembered when we started this class, I asked you all for a number between 0 and 100, and I asked it to be in integers as part of a Get to Know You survey. This is where that come into play. So the very person who responded to that survey said their favorite number was 88, or the number that they selected, and 13 came up a lot. So that was why I picked 13. And we're going to try to find those percentiles using properties we're going to try to just find those percentiles. Okay, so let's talk about, we'll do the 88th first. Okay, so with the 88th percentile, we can look over here and we want to find the value at which 88% of the observations are below. So if we look over here, and remember CDF is the probability that x is less than or equal to little x. So it is the lower area probability with boundary value at little x. So let's go to like 0.88 is what we're looking at. So the value on this function the input of this function that corresponds to 0.88 tells us, so we want 0.88 here, gives us the percentile value that corresponds to that. So this is 0.88 approximately. And it's somewhere over here. And we can find what X value that was that got us there. So to do this in another way, so I just did it with the plot really quickly, but let's do this a little bit more mathematically without the plot. So I have 0.88. I'm setting that equal to f of x. That's what I have there. I want to find the x value in this function that corresponds to 0.88. So I'm looking for this x, which x corresponds to the 0.88th percentile. So this is 1 minus e to the power of negative x. Should do a little curly x, symbolize lower. And we just solve for x. So I'm going to do exp negative x, adding that to both sides, 1 minus 0.88. And then I'm going to take the natural log of both sides. Now in stats, I know some math people might cringe at this, but in stats we denote the natural log log. So that's our natural log. So this value is going to correspond to the 88th percentile. It's going to be this value right here. And I did that on the calculator already, and I got 2.1202. And let's get the next value, which is the 13th percentile. Again, it was just a number that came up a decent amount of times. So I would go over here, somewhere over here, closer to half. Okay, so this is 0.13. That's where f of x is equal to 0.13. And then I would go, okay, what value x gives f of x 0.13? And I want to find that value. So it actually followed the same steps that I did here. I would do 0.13, and I'm going to set, this is also a set it equal to f of x and solve for x. 1 minus exp negative x. And then if I continue on, then I'm going to find that x, and I also did this in the calculator already, it was equal to 0.1392, which was kind of cool that it was like 13 and 13, well, almost 13. And that was our orange point. So that was 13, and this one was 0.8. Now, it said to simulate 33 values from the distribution above using a uniform 0, 1. So what I meant by that was do the same process over and over again. Look at values, so simulate values over here, uniform 0, 1 values, and then keep following the steps and follow the x's that correspond to those values. Now, um, I said 33 values because that's how many people responded to the welcome survey that I had. And again, I asked you to generate numbers between 0 and 100. And I was hoping that it would be quite uniform by me doing that. But as you will see, it was not. So I have the blue line represents that 0.88th percentile, the first person that responded. And we did pretty good. And then the gold one represents the 13th percentile. And it turns out a lot of you have the same favorite number, and most of you have numbers that are quite small. So then I actually simulated uniform random numbers and did not ask people for it, but I used a computer to give me a bunch of numbers. This is also 33 values. You can see it's a little bit more spread out and diverse. But we see a similar sort of phenomenon that I was describing earlier with this in the previous video, where you have these values that have percentiles that are quite close, but if you were to follow these lines, they're very, very, very close. And then where they mark on the graph is quite far apart. And it's this natural sort of thing that happens with CDFs and those values is, yes, everything on this CDF, all of these lines that you saw that were randomly generated, they really are evenly dispersed along the y-axis. But this function creates a different type of dispersion that matches the random variable that we're looking at. So if I were to generate values here, perfectly uniformly random. They all have the equal opportunity to be selected. And I continue through this process, then the values that we get to, using the inverse of the function will correspond to the right values for this distribution and be spread out appropriately. So you look at the graph and it's really very sparse out here, but it's also very close to -1. Like this is already near the 99th percentile. Let's just be like 0.9999 percentile. We shouldn't have that many values out there. So it's going to disperse it the right amount for this distribution.